Well, welcome back, and we're going to have like just this short session to finish up the last notes handout. And it's on, of course, right here, what it says, Notes and Problems with the Boussinesq Approximation. And previously we mentioned that there's a Knudsen number, right, Kn, and that must be small, and we were looking at it with the molecular analogy, which is sort of trying to put this Boussinesq hypothesis on some better grounds from a molecular to turbulence or continuum analogy. And, you might also argue that near the wall, this would break down anyway, because near the wall, you have particles and the roughness length near the wall might be on the same order. But that's a dicey business. And in fact, there was a huge new call, Amiri from the United States Air Force and Navy to look at boundary conditions and porosity, $1.5 million a year for 5 years for a new university program to try and improve turbulence models of porosity and roughness. So it's still an area of a lot of money and a lot of research if you're good and can break into that part of the field. Anyway, one thing that we should take away and remember in the next section is that these length scales arguments go as a partial u, partial y, all over partial u2, partial y squared. And also near the wall, we said that the length scale goes as y, like in equation 4.11, which we had earlier in this section. Now, another way, remember, to look at the Knudsen number might be to look at, say, there's some integral scale again, and maybe some mixing scale. And if Knudsen number is going to be small for a continuum flow, for these flows to apply, then this should be small. And we'll just say less than 1. And it turns out that in incompressible turbulent boundary layers, this value's on the order of 0.41. And you'll also notice another value is very close to 0.41, which is the von Karman constant, which people often set to 0.41 in many practical flows. Another way to argue about this is that we might have L mixing goes as some mixing velocity scale of the same divided by just the magnitude of du dy. Y, so you have dimensional units, right, of meters. And this particular equation might tell us, when you look at that graph of P and Q in particles in space, that would say you have P and Q and how fluid travels around, that these lumps of fluid that Prandtl was arguing about might be able to go to one each other as you go downstream. But it turns out that in turbulent flow, that might be just sort of some more flimsy hand waving. So this analogy doesn't really work. From particle viewpoint to turbulent continuum flow. And I'm going to note a quote from Tunicus and Lumley. And they wrote in their book on Introduction to Turbulence that they wrote, the general conclusion must be that turbulence in a shear flow cannot possibly be a state of equilibrium, which is independent of the flow field involved. So you'll make another note that these models that we've looked at assume that turbulence is in equilibrium. But it turns out in shear flows and say boundary layers, we aren't really in equilibrium. and the flow is not truly statistically stationary. In fact, one might just say that the turbulent flow is always trying to change and evolve because of some external forces or body forces or boundary conditions. And but we kind of hold this assumption anyway. So some interesting, just some points I want to write down over this whole last section, that these eddy viscosity models especially algebraic ones, have been used and tuned from 1925 to the 1970s. And that's where we're going to really pick up with Cebeci-Smith, which is like the culmination of 50 years of research, which led to a very practical model. And the amount of empiricism you're going to see when we look at the Cebeci-Smith model is quite amazing. And we're going to go fast and say, okay, there's all these different equations, and behind every little equation, there is some kind of measurement study or sort of scaling law study. Well, most turbulence researchers, even today, make the equilibrium assumption, which is very important. If not, then you have a non-equilibrium turbulence model, and those are less prevalent, but you'll find them in the literature and in some codes, not usually commercial type CFD codes. And almost all the models of this era, which were practical, used the mixing length hypothesis. And so even more complicated models under analysis could reduce to them. So sometimes someone tried to propose something new in the algebraic model world, which is advantageous because they run really fast, but then they would just, could be shown later to kind of reduce to a mixing length analogy. Well, and so why is this? Because in all these algebraic models, they're incomplete. There's no complete algebraic model. And that means that we specified something about the flow in advance. And I can always specify length scale as a function of distance to the wall and the boundary layer. But what if I specify something else, like time scale or velocity scale? Well, it turns out that if you do a length scale model, I can always recover these other scales. So if I do, say, a time scale model, I can always recover length. So we always go back to length scale, I suppose, because it's a very physical thing about the boundary layer, that as I go away from the wall, my turbulent eddies should increase in size linearly and then even out in terms of like a constant far from the wall. And that's what we're going to see as the starting basis of the Cebeci-Smith model, which does then use the Van Driest type equation for using an exponential function to make it continuous.